Hi guys, we'll talk about glomerular filtration rate today. So what is GFR? Before going to that, what are the components of this filtration membrane? All these things we'll talk about. So the glomerulus will get its blood supply through afferent arteriole, and from there it leads to the glomerulus, which will be located in the Bowman's capsule. So the blood will be filtered from the glomerulus into the Bowman's capsule. This is called as filtration or glomerular filtration rate, and whatever that excess blood is there, that will be drained through efferent arteriole into peritubular capillaries and then into the renal vein. So the first event in urine formation is filtration, then there are other events, reabsorption and secretion. Our concern for today is only filtration, so we'll talk about GFR. So what is GFR? So it is the amount of filtrate formed by the glomerular filtering membrane of both the kidneys in unit time. So what is that unit time? It may be minute or day. So usually it is 125 ml per minute. If we make it for day, 180 liters. And the better indicator for glomerular activity is filtration factor, because it is based on how much plasma it is getting. So GFR by renal plasma flow is called as filtration fraction, and usually it is ranged from 0.16 to 0.2, and it is the better index of glomerular activity. And coming to the filtration membrane, what are the parts of this filtration barrier? One is the endothelium of the glomerular capillary, and that is fenestrated. Fenestrated means it will be having holes. The endothelium will be having holes, and a basement membrane, then epithelium which contains podocytes. The cells of this epithelium will be having foot-like process, that's why they are called as podocytes. Podo means foot, and in between these podocytes there are spaces called as slit pores. So here is the filtration membrane with fenestrated endothelium of Bowman's glomerular capillary, and in between there is basement membrane fused with the basement membrane of epithelium which contains podocytes, and in between these podocytes we will be having slit pores. This is the filtration barrier through which the blood is filtered into the tubule. Coming to the determinants of GFR. GFR is equal to filtration coefficient into net filtration pressure. So what is this net filtration pressure is glomerular capillary hydrostatic pressure minus Bowman's capsule's hydrostatic pressure minus oncotic pressure of glomerular capillary plus oncotic pressure of Bowman's capsule. Okay, I'll make that clear. So this is the Bowman's capsule and this is the capillary. Okay, so whatever the hydrostatic pressure here in the capillary is plus. So this is the capillary hydrostatic pressure of glomerular capillary. So it tries to push the blood out. Then the capillary pressure of or hydrostatic pressure of Bowman's capsule, whatever the pressure here, opposes it. So it is minus. And the oncotic pressure of capillary will oppose the filtration. That's why it is again minus. And the oncotic pressure in the Bowman's capsule or in the tubule will favor the filtration. That's why it is plus. So the sum and minus of these pressures is called as net filtration pressure. And what is filtration coefficient? Filtration coefficient is nothing but it is the product of capillary permeability into effective filtration surface area. So with this we can say the factors affecting GFR. Simply, one is hydrostatic pressure. So Starling force is 1, hydrostatic pressure, 2, oncotic pressure, and 3, capillary permeability, 4, surface area. So by this we can know almost 4 factors. And explaining this net filtration pressure here, so this is the afferent arteriole which has a hydrostatic pressure of glomerulus 60 mmHg. So we have 60 which is favoring out. Okay. Then glomerular colloid osmotic pressure is 32. So that is opposing. So minus 32. And Bowman's capsule pressure is 18. That is also opposing. So minus 18. And literally there will be no protein in the Bowman's capsule. So oncotic pressure here is 0. So plus 0. Totally we are getting a net filtration pressure of plus 10 mmHg. So plus 10 mmHg of net filtration pressure. So we got plus 10. So that is favoring the filtration. Now coming to the factors. Already we mentioned the factors. We will again talk about the other factors which can be added. One, GFR is dependent on renal blood flow. So one is blood flow. Then glomerular capillary hydrostatic pressure. So this is plus, this is plus. Capsular hydrostatic pressure opposes. Oncotic pressure of capillary opposes. Glomerular capillary permeability. More the permeability, more the GFR. Effective filtration surface area. More the surface area, more the filtration. Size, shape and electrical charge of the molecule. So smaller size favors. Negative charge repels. Shape, filamentous, more filtered. So renal blood flow, as we already mentioned, it is directly proportional. So vasodilation of afferent arteriole will increases GFR. Capillary hydrostatic pressure, definitely it is a plus 1 plus. So it is determinant on blood flow as well as drainage. Okay, let us see here. This is the afferent arteriole and this is the efferent arteriole and this is the Bowman's capsule. Let us think that. So if this is dilated, means more blood comes here into the glomerular capillary, glomerulus. And if this is constricted, less will be drained out. So majority will be filtered. So these are the two factors, either afferent arteriole dilatation or efferent arteriole constriction favors or increases the GFR. And efferent arteriole constriction much will decrease the venous return to, and that decreases GFR. So threefold rise in efferent arteriole constriction will decrease GFR. Coming to the capsular hydrostatic pressure. So if the hydrostatic pressure in the Bowman's capsule, let us think that here the hydrostatic pressure, let us think there is a stone here blocking the tubule. So the fluid accumulates here. Now the pressure here increases, which opposes the filtration from the capillaries. So inversely proportional, as seen in tubular obstruction. Oncotic pressure. Now oncotic pressure is glomerulus is inversely proportional because oncotic pressure tries to keep the fluid in its own compartment. So glomerular oncotic pressure tries to keep the fluid inside. So hypoproteinemia, whenever protein is reduced, oncotic pressure is reduced, so GFR increases. Similarly, dehydration, relatively the protein increases, so oncotic pressure increases, so GFR decreases. And coming to the glomerular capillary permeability, directly proportional and effective filtration surface area. More the surface area, more the filtration. And the mesangial cells which are surrounding these glomerular capillaries can contract and they decrease the surface area, decreases the GFR. Coming to the size, larger the size, less the filtration. So inversely. Shape, slender will be filtered easily than spherical. Negative charge is less filtered because the porocytes and the basement membrane will repel the negative charged particles. So positive charged particles are attracted and filtered much. So that's why albumin, even though it's a smaller molecule, because of its negative charge, is not filtered. Coming to the measurement of GFR. GFR is measured by the principle of clearance. And what is clearance? volume of plasma from which a substance is cleared in unit time. So clearance of a substance is equal to urinary concentration of that substance into volume of urine collected by plasma concentration of that substance. So UV by P is clearance. And if we take a substance which is only filtered, neither reabsorbed nor secreted, we can get the GFR. So such a substance is inulin and creatinine. And there are criteria for this indicator or substance. One, should be easily filtered, neither reabsorbed nor secreted, and it is not metabolized by the body, not synthesized or stored in the kidney, non-toxic, and estimation of plasma and urine concentrations must be easier. Coming to the regulation of GFR, so it occurs by three ways: sympathetic, hormonal, and autoregulation. So what is sympathetic nervous system's regulation? So simple. Mild sympathetic stimulation doesn't affect any GFR. But if there is an hemorrhage or ischemia to the CNS, cerebral ischemia, or in-flight fight response, what happens is intense sympathetic discharge will be there, and that causes renal arteriolar constriction. We know that if the blood flow is reduced, GFR is reduced. So decreased renal blood flow, decreased GFR. So more the sympathetic nervous system activation will get decreased GFR. Coming to the hormonal, simple. Whatever that causes vasoconstriction decreases the GFR. Whatever that causes vasodilatation increases the GFR. Norepinephrine is a sympathetic one, vasoconstrictor, so decreases GFR. Endothelin, vasoconstrictor, decreases GFR. Adenosine, usually adenosine is a dilator everywhere, but is a constrictor in renal. So that is also a vasoconstrictor, decreases GFR. Angiotensin usually is a vasoconstrictor, but more of efferent constrictor than afferent. So that favors GFR. So increases the GFR. Prostaglandins, again dilators, so increases GFR. Nitric oxide increases GFR because it is a vasodilator. And prostaglandins and nitric oxide, what they will do is they counteract the effect of catecholamines and angiotensin on afferent arteriole. So they maintains the diameter of afferent arteriole more than that of efferent. That's why afferent arteriole will have more diameter than efferent to favor the filtration, because prostaglandins and nitric oxide are more in the afferent arteriole. Atrial natriuretic peptide also increases the GFR. Coming to the autoregulatory mechanisms, occur in between 75 to 160 mmHg of mean arterial pressure. Why this autoregulatory mechanisms should occur? Let us think that our BP has increased. So more capillary hydrostatic pressure, more GFR should occur. We will be losing more volumes of water from the body. So more blood volume is lost. Such a thing shouldn't occur with fluctuations in the BP. So if that happens, will be leads to depletion of blood volumes. So to prevent the loss of that huge amounts of water, GFR is regulated in between 75 to 160 mmHg. Beyond that or below that, it is out of its regulatory mechanism. And the autoregulatory mechanisms are two. One is simple intrinsic myogenic mechanism, and another one is tubuloglomerular feedback mechanism. We'll talk about this myogenic mechanism. Myogenic mechanism is simple intrinsic. So whenever the BP is increased, that causes stretch of afferent arteriole. So more the BP, more the blood flow, more the afferent arteriole stretch. That releases stretch induced calcium channels opening. So whenever calcium channel is opened, influx of calcium occurs. So influx of calcium causes constriction of the arteriole, so decreases GFR. So increased blood pressure is finally should increase the GFR, but by the myogenic mechanism it is constricted and decreasing the GFR. And the other mechanism, tubuloglomerular feedback mechanisms, is mainly based on juxtaglomerular apparatus. We know that Juxtaglomerular apparatus, where the afferent arteriole's epithelium is modified into juxtaglomerular cells which secrete renin. Okay, and the the cells of distal convoluted tubule are converted into macula densa, which acts as a receptor for the change in the volume, BP and sodium levels. So macula densa is the receptor and juxtaglomerular cells are the renin cell secreting cells. Now we'll talk about this. So let us think that the BP is decreased. So whenever the BP is decreased, we know that GFR is decreased. So whenever the GFR is decreased, the flow of sodium chloride to the macula densa is also reduced. That can occur in another way also. Whenever there is more proximal sodium chloride reabsorption, when this maximum proximal sodium chloride reabsorption occurs, if the glucose or protein is more, so sodium glucose, sodium amino acid transport import will be more in the PCT. So that leads to decreased sodium chloride at macula densa. Now the macula densa thinks that the body is having less sodium, and the macula densa also thinks that the GFR is lowered. So even if it is more reabsorbed, GFR is lowered, it thinks. So what it has to do? It has to increase the GFR. So it has to counteract this decreased GFR and it has to increase that GFR. So we already know that by this macula densa activation, it activates juxtaglomerular cells that secretes renin, which acts over angiotensin nogen to form angiotensin, and that is converted to angiotensin 2 by angiotensin converting enzyme. I already mentioned angiotensin is a vasoconstrictor, but more of efferent. So vasoconstriction in efferent will be more and less on afferent. So this is happening. More dilatation of afferent, more constriction of efferent, and Bowman's capsule, more filtration. So the GFR is increased. Let us think that GFR is more. Now the contraction should be decreased GFR. So increased sodium load in the DCT. So more the sodium reabsorption. How it occurs? By sodium potassium pump activity. So more ATP utilized. ATP is broken down into ADP, AMP and adenosine. So adenosine. I already mentioned adenosine is a dilator everywhere but a constrictor here. So afferent arteriole is constricted. So blood flow is reduced. So GFR is reduced. In this way, GFR is regulated by tubuloglomerular feedback mechanism. Thank you for your patient listening. Bye.